There is a question here. About rectangular and triangular elements. Yeah, in general, right now, we have both. We can discretize, we can partition a domain using both rectangular and triangular element. But it's not neither rectangular, it's quadrilateral. So you can have something which is not exactly a rectangular. But also you have, definitely you need triangular, because as I explained before, right, there are lots of cases when you have these corners and we need triangular elements. So now, yes, you can combine. So use this, and that. And also you can combine, for example, use plate elements and also beam elements, patient. But the idea right now is that all of that comes after you have model the structure. So you see the structure and you, for example, you say, I propose, I'm going to analyze this as a beam. In the case of the pedestrian bridge, for example. If I am the one who is going to supervise your work, I can say, okay, this is a very preliminary calculation. That's all what we need so far. And I can solve that in half an hour. If we go, for example, we try to check that everything is in detail and all of that, and I'm going to tell you, now, I need to model that in detail with plates and applying the loads in the center of each one of these panels. Then it will take much more time, of course. And remember that the thing is not only to do prepare the model, the finite element model, and get results. The last step is, the most important, is analyze results. I'm going to mention that in a second. That was one comment here. Can be the transfer plate be simplified as a flat bar? Yes. Yes. So you can replace, for example, the deck plate as plain elements, and then the reinforcement on the side, and also the transfer reinforcements as beams. Yes. You have to be careful with that, okay? Because remember, when you have a beam welded to another plate, the two bend together. And in that case, you have to consider, for the inertia, you have to consider the effective breadth. Be patient. We're going to go in these steps. But the answer to that is yes. And what's the advantage of doing that? Because in that case, you can reduce the number of joints. That reduces the size of the problem. Of course, that's an advantage. Okay. Yeah, there is another question. Anybody has another question?
Yes.
Go on.
Yes, I am Karen.
Yeah. Please, okay. Don't use your first name. Use your last names. You are Kumbe. Go on. Kumbe. Go on.
Okay.
Go on.
It said that different analysis in the beam or the plate, the difference can be a vector displacement. El vector displacement is the vector displacement, the coordinates direction.
Yeah, I know. Okay, I can say a couple of words about that. I have to share the screen, right? Yeah, that's what here. I didn't say that we have 17 unknowns. I said we have 17 joints. Now, if we have all the plates in one plane, for example, here, let me go back. Here, for example, see, we have all the plates in the same plane. So we were interested only in the vertical displacement. Okay, but here, it's different. Okay, So for example, if we have, this is the deck plate, right? The vertical displacement, let's include a reference system. So this is X, and this is Y, and vertically that's Z. Okay, for example, this joint here, which is part of this plate, moves in this direction. That's important for him. But for this element, which is this transverse reinforcement, this plane element is in the plane YZ. So if this element deforms in this direction, that's going to be lateral deflection for this. But this direction is going to be in plane deformation for this plate here. Okay? We have to do is, we have to set up what we call a global reference system. And what we're going to do is we're going to take components of this displacement for every one of these elements in this reference system. We will see that, don't worry. But yeah, in this case, what we're saying is that every joint can move in the X, Y, and Z directions. So right now, each one of these could move in 3 directions. So we would have 51 unknowns. Okay? But yeah, that's something that we're going to go. We are going to start analyzing, for example, a beam in an XY plane. But the problem is that we could combine beams in 2 directions. And in that case, we have to find a common reference system. It's what we call a global reference system. Be patient. And what we're going to do is we are going to set the equilibrium equations in this common reference system. So everybody will understand the equilibrium. Cumbe? But yeah, we're going to do that.
Thank you.
No problem. No problem. Okay. Let's go on with this. We're going to say a couple of words about general steps in the finite element method. Okay? General. So the first step is discretize. Now, this is something that we have mentioned here. So the first step is we have to discretize. Okay, this is something that we have done here. And of course, we have to select element types. In this case, we are selecting only plane elements, quadrilateral plane elements. In the first model, we use only beam elements. So what I'm trying to say is that this comes after modeling the structure. So, for example, if I want to model this as a beam, then the discretization will be putting joints only in one line. And the elements that we're going to be using are the only beam elements. So you see that the discretization is related to the model of the structure. That's the first step. Let me include more space here. Let me save a little bit here. There. Okay. That's the first one. Second one. Okay. Remember that the discretization imply an interpolation in every element. So what we have to do is select the displacement function interpolation. Okay? Don't worry. When in the first part of the class, I'm going to ask you to do these steps manually. Okay? So in this case, we have to worry about this function. In a couple of months, we will be using ANSYS. And you will see that you don't worry about that. But that's why I need you in the first part to think about these things. Because when we go on with using the ANSYS, we just forget about that. But this is something that we have to have in mind. Okay? We use interpolation. That means that this is a possible source of error. Okay? The third step, remember that we're working with structures. So we have to say a couple of words about stresses and strains. So we have to define the following relations. We have to define the strain in relation to the displacements. So here, please, in the second step, you set up the displacements. And with the displacement and these relations, you can get strains. Somebody remember epsilon x? What's the definition of epsilon x, people? Anybody? What's the definition of epsilon x? Somebody? Anybody?
Delta x over x.
The derivative of u with respect to x. So we're going to say is that that's du dx. This is u. Now here, when you select the displacement, you are going to say that we can calculate u, v, and w. And here, when you define these relations, using this u, v, and w, you can calculate strains. Anybody? Gamma xy? Anybody, please? Anybody? Gamma xy?
Du over dj.
Du dy plus
Yes, more dv over dx.
yes. And you see that if we set up these displacements with this interpolation function, this is an approximation. We remember these definitions, these relations, and we can calculate strains. And then with these strains, we may calculate stresses. Anybody? Sigma x related to epsilon x? Anybody? Remember? Anybody?
More for x? No?
Yeah, but that's only for one case. In
Okay.
general, it's more complex than that. Okay, so it's, I'm going to write it like this in the unidirectional case. Okay, that's going to be easy. That's going to be the relation for the beams, because in case of beams, we usually use only we usually worry about only sigma x. But in the case of the plates, we have to combine sigma x, sigma y, and epsilon x, epsilon y. Okay? And in that case, we need to include nu aspect ratio, the Poisson ratio. Okay, that's the, and we're going to be in the linear region. So this type is going to be constant. So I have to tell you that we are going to be working in the linear region. We are not going to go beyond the elastic limit. This is enough. Next step, that's the fourth. We have to derive the stiffness matrix for every element. So for example, here, it's easy. This is a beam element, for example. Okay? In a beam element, you are defined by this and this joint. And in this case, we have external forces and moments. So let's suppose this is external force, external moment. External force, external moment. And in our case, we're going to be using one method in chapters 2 and 3, what we call the direct method. And using equilibrium, we're going to transform this into this. A matrix, what we call like that. And that's going to be multiplied by the displacements. For example, it's going to be D1Z. No, D1Y, I'm sorry. This is Y. Then with one phi 1Z, D to Y, and phi to Z. Okay, so you can see that these are the displacement and rotations of the two joints which define this element. And on the right-hand side is we're going to have external forces. We're going to have F1Y. So this F1Y is this one, F1Y. Then we're going to have M1Z. This M1Z is this moment that is applied here. And on the other joint, we're going to have F2Y, M2Z. And what we're doing is ensuring that this joint and this joint are in equilibrium. Okay? That's the easiest way to reduce the stiffness matrix. So this matrix here is what we call the stiffness matrix. Of the element. Okay, so we take this element, every element, and we recognize that in this case, this is just for one beam element. This is something that we're going to be doing in chapter 2. We have 1 and 2 joints. These are the external forces, people. Remember, external forces, internal forces, that's something that we have to recognize. And what we do is we convert the equilibrium of this element and we express it in this way. So this stiffness matrix is completely known. In here, you are going to have Young modulus, inertia, length. So these are the unknowns, 4 unknowns. And this is something that we should know. That's the forces on the joints. External. These are external. Don't worry, we will study this in detail in next session. So this matrix is the stiffness matrix. Remember, this is 4 by 4, this is 4 by 1, and the result of that is a vector 4 by 1. Okay? Once we have that, we can go on and we can combine somehow all the matrix, stiffness matrix for every element to form what we call the global stiffness matrix, or I'm going to write it like this, very large G, because it's a large matrix. So what we have so far is, let's suppose in the case of the beam, so we have something like this. Let's suppose we have 3, right? So for this one here, we have K1, right? Multiplied by the displacement vectors and equal to the forces. We have another one for this. It's also little k, or this is for element 2. For example, this element here could have different lengths than this one. So in general, this and that are different. They're constants, completely known, but could be different. Multiply by the displacement and equal to the forces. I'm not going to write for the third one. So we have this, and that are the joints. Okay, and what we have to do is we have to combine this thing here. And we're going to be using what we call continuity and consistency. We will explain what this is. And you can see immediately, this point here moves vertically, right? So this motion, this vertical motion, is going to be considered for the equilibrium of this element. But also, this joint is the first joint of the second element. So the displacement of this element, of this joint, which is part of this element, has to be equal to the displacement of this joint, which is part of the second element. That's what we call continuity. Here we have a vertical force. This vertical force, external, is like has to be splitted. Part of that will be required in order to equilibrate this element. And the rest is going to be employed to equilibrate the other one. And that's what we call consistency. Don't worry, we will explain that in detail. What's the result? The result is we're going to have a very large is what we call big K. It's a large matrix. Here, I don't use a hat because it's for everybody. Large F, no hat. This is big K. Okay? Does anybody remember what's the algorithm to solve this type of equations? Anybody? Anybody?
The inverse matrix?
No, that's a procedure. It's inverse. See, I remember I think it was the year 2011. And it was a very, very good year because I I was able to direct, I think it was 3 graduation work. And in one of them, I'm trying to remember the name, the name of the engineer Jungan. And we were able to model the structure of the whole corvette of the Ecuadorian Navy. We employed, I think it was 300,000 degrees of freedom. So this system here, in that case, would have this matrix, it would be 300,000 columns and 300,000 rows. That's a big cake. Okay, of course, these are the unknowns, and these are knowns. Okay, so this is a big problem because you can use, for example, very small elements. And the problem is that in that case, the number of this, the size of these arrays is going to be very large. And of course, that takes more time to solve them. So we have to be very, very clever in discretizing the structure. And then the next step, this was what? 5. The 6th. Of course, it's a solution. What we do is we find, so these are the displacements of every joint. See, when you solve this, okay, when you solve this, you know how much this moves, this, and that. Now, we have to go back. Why? Because we want to know how much are the stresses here. And for that, we need to evaluate bending moment and shear forces, right? So the next step, using these values, is I have to insist for every element we have to calculate strains and stresses. Something that I forgot, and it's extremely important, is that in order to solve this system of equations, okay, in order to solve here, we need to include the supports. The supports are basically boundary conditions. Remember from your differential equations class, if you do not have enough boundary conditions, you cannot find a unique solution. Something equivalent to that can happen if you do not include enough supports. And that's quite common because we usually tend to forget that in general, okay, but by default, the analysis is a 3D analysis. For example, if you have a beam like this, you say the displacement in this direction is 0. Yeah, but the beam can move in that direction. So you have to say, okay, it can move in this direction, and it can move in that direction, and it can move in this direction either. So if you do not include all of these conditions, you're not going to be able to solve the problem because in general, that's a 3D analysis. We will insist on that. Okay, and after that, let me use a different color because I think this is the most important. is what? Is analysis of results. Do they make sense? For example, you can check that the stresses in a certain area are positive. Make sense? In a certain area, these stresses are very large. Do they make sense? Is that what you expect? Another thing that we need to do here is convergence that we discussed before, right? Remember, finite element is extremely powerful tool, extremely powerful tool, but it's not exact. So in our mind, always should come the question, how close am I from the exact solution? That's what we have to say something about this. We don't have to worry much about this because some of the steps, when we start using ANSYS, some of these steps are completed by ANSYS, but some of the steps are our responsibility as engineers. So in general, I would say step one definitely is ours. So we're gonna need, let me use this. So this is the engineer. Don't doubt, this is ours. Once you start ANSYS, using ANSYS, you tell the program you want to use this or that element, right? And then we'll have predetermined the displacement function for interpolation. So we don't have to do that. He uses. You have to remember that this is an interpolation. This is a simplification. It's not exact, but that's all. He has all of these relations, so he's able to calculate strains from displacements and stresses from strains. To calculate that, of course, we have to give them the mechanical properties. But that's all, okay? Maybe we should put this in here. In general, mechanical property is something that we have to specify. This is something that he does internally for every element. This is something that he does because we have to specify how these elements are connected. This is something that we have to specify. This is something that we have to specify. So we have to tell the program what the forces are acting on the system. Could be concentrated, could be distributed, etc. This is extremely important, the supports. Remember, supports in finite elements is what we consider in differential equations as the boundary conditions. And definitely, this is us. It's something that we're going to insist in the project at the end of the semester. See, you can see that you sit on the computer, run ANSYS, and you will have many numbers. You can plot these results with lots of colors and everybody will be impressed. But that's not the end. You have to analyze that. That's our job. Okay? Any questions about this process, people? Any questions about? No? Okay. We have some minutes, So we can start the next subchapter. So next subchapter is 1.2, is what we call the stiffness matrix of a bar. Let me put it with capital element. Okay, and we're going to be using the direct method. Okay, and there are several ways to deduce it. Okay, so that's why I have to insist that the method that we're going to be using is the direct method. Let me save this there. Okay, so in this chapter, we're going to be doing some simplifications. We apply these simplifications. First, the displacements and strains are small. So, for example, when you calculate the strain, you say delta L divided by L, right? If you have something that elongates, the strain is, normal strain is delta L over L. And you wonder, the L is the final or the original L? There's no difference because we are, in this case, we're assuming that the displacements are small. So for example, we say del epsilon x is the elongation divided by L. And this is more or less equal to delta L divided by L. Because the difference between the original and the final length is negligible. Why? Because we're assuming that displacements are small. It's typical of our analysis, okay? What else? We assume that we work with material in the elastic range. So we can say that sigma x is equal to E epsilon x for the case of the single displacement case, unidirectional stress case. So in this case, we're going to need E and nu. And of course, you know that with these two, we can deduce G. In general, the bar element is considered as a element with constant section. Okay, so the deductions that we're going to present are going to be using this assumption. You immediately think, okay, what happens if I have a bar which does not have a constant section? Well, what we can do is we can split it in several elements, and in each one, you can take the section as constant. So there's no such a big problem. And also, this is something that, remember, this is chapter 1. If we consider a bar is a long element which supports only loads in the axial direction. So a bar, it's a long element which support axial load. Okay? Now, you can immediately see that these two assumptions means that the system or the analysis is linear. Okay, so our analysis will be linear. We can use finite elements to do nonlinear analysis. For example, we could go beyond the elastic limit, but that's more complex to analyze. So we hold it for grad school. For undergraduates, as you are, this is enough, okay? This is something which is not limited, since we could, for example, we could, as I said before, okay, if you have a bar which changes in section, what we can do is we can split it here in two elements, right? And in each one, the section will be constant. So this is not such a big problem. So from here to there, we have constant section, and from here to here, we have different constant but different section. And we could analyze this in this way. Or we could go on and analyze it as a plate. But right now, we need to analyze bars. And of course, the last one, this is not really a simplification. It's like considering the type of loads that we're going to be working, okay? So right now, if I have an element like this, okay, I have to consider forces only in this direction. And this is what we call a bar, okay? If I have something like this is lateral load. And in that case, what happens? The system or this element bends. That's a beam. That's going to be in chapter 2. Don't worry, we will study this case, but not now. Now it's only this one here. The forces will be aligned along the bar. Okay, let's go into matters. Let's deduce, this is just a reminder. Okay. So let's consider a long element supporting a force in the longitudinal direction. Supporting, no efforts, forces. Let me erase this. Okay, supporting forces in the longitudinal direction. So we're saying is that we're analyzing something like this, very long, and we have forces like this, forces like that, okay? This is the X direction. Let's see, this is force I or J, and this is force 1, whatever. In static equilibrium. So if the system is in static equilibrium, I can say that any piece of that is in static equilibrium. Okay, let me complete this. So let's suppose that we have little forces like this distributed on the bar. So let's take one arbitrary element. So this element has length dx. So this is an arbitrary element. So what we say is, okay, let's consider that this element is in equilibrium. Okay, this is the x direction. So this cut, it's at the position x. Okay, since we are considering that the section is uniform, we can assume that we can take one single force on the left section. This is the internal force. Remember, this is the left face, negative face. This is the positive face. In the negative face, the positive internal force points in this direction. This is the positive face. So in the positive face, the internal force points in this direction. But not necessarily is the same as this one. So we're going to have the force on the left and a little change. And that little change is related to this is force per unit length, as we have shown here. So these three actions has to be in equilibrium. So they have to cancel. So we have one force to the left, one force to the right, and one distributed force on the element. So they have to cancel. We're going to go on with the equilibrium of this in the next session. Okay. Any questions about the assignment, people? Any questions about assignment?
Doctor,
Yep.
in the exercise 1, the
Okay.
method of the bisection.
Bisection. Okay, go on. No problem. No, don't say to say, excuse me.
We obtain the different figures or one figures and the results the friction or all the figures with each Reynolds and coefficient.
Did you take a ship machinery too?
Excuse me?
Did you take the course marine machinery too?
Yes.
Do you remember how these results were presented? Did you remember that this F, friction coefficient, was employed to calculate pressure drop in a pipe? Do you remember that?
Yes.
Yeah, come on. Yes, exactly. So you see that you use that in marine machinery too, and you have a plot, and you enter in that curve, in that figure, with the Reynolds number until one of these curves, which has the adequate roughness ratio, and in that curve you turn to the left and you read the value of the friction coefficient on the scale, right?
Okay.
So what I need you to do is use this program in order to obtain these values of F. So you plot these curves. So you have to have something similar to what you used in marine machinery too.
Thank you, Doctor.
Okay, that's something that, so Go on to Marine Machinery 2, remember those values, these curves, and try to plot something similar to that, okay? And you're going to see your results against the gringos results, and they have to be close.
Doctor, similar question. The first topic is about have the two variables. For example, Reynolds and coefficient friction. It's necessary. I have two variables.
I gave you a range of values for the roughness ratio, epsilon divided by D. I mentioned those in the seed web. The range of the Reynolds number, you have to select it according to the turbulent conditions that we are working. So this is turbulent flow. This is the application. So according to since it is a turbulent flow, you have to select an adequate range for the Reynolds number. And I gave you the values for the roughness ratio that you have to use.
Doctor, it's about the Reynolds here. We can relation we spent. We can I have all kind of spend length, very length. Is correct?
No, you don't see. What you have to do is you have to take values of the Reynolds number. Let me here. Can you see the screen? You have Reynolds number here. Take values of that. And you have the roughness ratio here, epsilon over D. I gave you values for this ratio. So I gave you this. You have to change, assume values for the Reynolds number according to the condition that the flow is turbulent. And then you go varying this Reynolds number, and you get for the value of the roughness ratio, you got this curve, and you plot some of this result in the same curve. You have Reynolds number, you have friction coefficient, you have several curves, one for each one of the roughness ratio. I insist, go to the class notes in Marine Machinery 2, review these curves and try to present something similar to that. And I expect that you include a comment comparing your results with the results that you can find in a fluid mechanics book.
Victor, I think I found a way to solve this problem, but I don't know if it's okay. So I want to ask you, because if this equation that is of Colebrook equation, we have three variables. So I take the roughness ratio like a constant.
Exactly. Yeah. See, what you do is you take the roughness ratio as a one value. See, I gave you, I think it was 4 or 5 values. Take one value.
Because
okay.
I take a reference, the Moody diagram, to select a curve. For example, I just take one value of roughness ratio like a 0.008.
I gave you, no. I gave you a group of values for the roughness ratio. Go to the seed web, and those are mentioned there. You have to plot friction function, frictional coefficient for those specific roughness ratio that I gave you. Now, for the Reynolds number, you have to vary that value in the range of the turbulent flow. I'm not going to tell you what's the range of the turbulent flow is. You have to find out.
Doctor,
I like to check.
Just a second. Let me see if I answered to the previous student. Zamora, I think.
Yes, I got you. Thank
Okay,
you, doctor.
no problem, no problem. Okay, next.
Doctor, good morning.
Yeah.
I have a similar question only to confirm about the in each method, for example, dissection method and Newton ransom, we will have several curve to each method, right?
They should be the same.
Yes, but to each method we will have several curves.
Yeah,
Right.
for each method, for example, let's suppose that I gave you 4 roughness ratios. So you apply bisection, you have 4 results. You apply Newton-Raphson, you have 4 results. But these 4 results from the bisection has to be exactly the same, well, not exactly, close to the result from the Newton-Raphson. The differences will be because the maximum error that you allow in each process are different. They should be close.
And what, how many values of Reynolds number we have?
You tell me, give me a suggestion.
I think that 6, I don't know.
Come on. Computing is so fast. At least 10 people, come on.
Okay.
If you have 10 values, you can draw something which is nice. You can see that if there are no breaks or something like that. Come on, it's, you see, what I would do is I would use 2 loops. In one loop, I would change the value of the Reynolds number. In the internal loop, I would take one of a value of the roughness ratio. That's it. Come on, you're younger than me. You can do that.
Doctor,
Yeah.
I have a question. If I take more values for Reynolds, I have a smooth curve, no?
Yeah. See, this is a continuous function, right? See, if you see these little jumps in the curve, probably is because the error that you are allowing is too large. So you have to go back and try to reduce the maximum error that you are allowing for the process. Did I answer your concern?
Yes, thank you.
Okay, no problem. People, let's be serious with this. If I see, I'm going to say that clearly. If I see any sign that somebody is copying the codes, you're in trouble. I'm enough with this. Everybody has to do its own work. Stay away from the border. Good day.
Doctor,
Yeah, go on.
question about my mate Jonathan. The good partitions in the range is about 20 or 30, or what's the best number?
See, the compute, I'm thinking about what I would do. What I would do is I would take 2 loops. In the internal loop, I would change the Reynolds number. In the external loop, I would change the roughness ratio.
But
in that case, the Reynolds number, you can change, I don't know, 20 times, and that's it. So at least I would expect 10 values, not less than that.
Okay, I got you. Thank you.
Okay. Please remember that you have to include comments. We're going to be checking that because we need to be certain that everybody is able to do a little programming. Okay, people. If you have questions about programming, the details of that, Miss Loyola can help you out, or Engineer Isaac, more than me. If you have problems with the algorithm, yeah, I can help you out. But about Python programming, probably they can help you more, because I usually use a different language for programming. Everybody has to use Python, no option. I warned you 2 weeks ago. Okay, people, have a nice weekend. Go away, key.
Thank you, doctor.
Thank you, doctor.
People. I need you to fill a form. Okay, I'm going to post it. Please do so. It's just 3 or 4 questions. I want to know where you are, if you have problems with the connections and things like that. It's just quite something very fast. Okay, try to do it as fast as you can, so we can have a good idea of where you are and all of that. Okay, have a nice weekend, people.
Doctor, I have own trouble about my certificate of vaccination, because I get my vaccine in USA and I tried to get the certification and I couldn't get my.
Now,
So
the thing is this. Okay, I understand.
I am doing the paperwork.
There's one thing here. Let me say. The thing is this. It's in your it's the first thing that we have to be certain here is that you are responsible for what you sign. Okay, this is the problem. You can assure me that you indeed get the vaccination in the US, but you didn't. Let's suppose that you are responsible for the possibility of contaminating everybody. So in this case, I can trust you, but I need some proof. Now, when you get the vaccination in the US, did you get any document?
Yes, I sent to him.
That's enough.
That's enough. I think
Okay.
that you want the certification. That
I know, but in your case, we can do an exception. There is no problem.
Okay.
But the thing is this, you are responsible for that. And when the time comes, I'm going to give you a form and you have to sign it, saying that it is indeed what happened.
That's okay for me. Don't worry.
There's no problem. I know. But that's the thing, that everybody has to be responsible, has to be aware that if we did not get the vaccine, we could contaminate the others.
Okay.
That's something that we have in our memory. Okay.
Understand. Bye-bye.
Bye now.
Doctor, one question about the present format, the homework. It's all the work in is the present in the program Python, or
see, you have to do. We need to check that you are able to prepare these small programs. These are very simple programs, okay? But we have to be certain that you are able to complete this assignment. So you have to explain in a paper how you did it. For example, in the case of the Newton-Raphson, you have to specify an expression that you employ, right? That's related to the derivative, right? So you have to write it here. But then you have to get the results and plot them. But also you have to send us the code because we need to check the code. So you have to send us both.
But the graphic, how the presentation in...
You can take the values and do some graph we use in Excel or something like that.
Okay.
Or you can find in Python, there are certain tools in Python. I was really surprised that you can find some tools in Python to prepare plots.
Mm,
It's really nice, really nice.
yes,
So
I
you can go
find
either.
I
Yeah.
find the routine, the plot, but I know how present the homework.
Yeah,
but
you have to include both. You have to explain us. Because if you present just the code, I'm not going to see, we are busy too. So we don't have the time to see what this code means. No, you have to explain how you did it. You have to present the results, make a comment, but also we need the code because we need to check that the code really works.
okay,
Okay,
thank you.
no problem.